Okay, there's two things on the screen. One is fake news and the other is an astronomical signal called the Lorimer burst, which is an example of a fast radio burst. And I'm going to give both a high level and a deep level description of these things. So we're used to the night sky, the optical night sky. The ancients used to think it didn't change. This is a picture of the southern hemisphere's night sky, and you can see the Magellanic Clouds there, and also the Molonglo radio telescope. In the radio sky, it was originally thought it didn't change much, but fortunately we had a woman by the name of Jocelyn Bell who had an intricate knowledge of her instrument in Cambridge, and she discovered these wonderful things called pulsars, which are discrete bursts of radio emission from rotating neutron stars. And when they were first discovered, their nicknames were LGM 1, 2, 3, and 4 for little green men, 1, 2, 3, and 4, because when the first one was discovered, it was like, could it be aliens? So I hate to repeat history, and fast radio bursts have been associated with aliens. They're probably not, but they have some characteristics which are interesting if you put your thinking cap on, and we're into out there theories at this particular meeting. So the radio pulses are not all the same amplitude. They're thought to be by a byproduct of the spin-down emission that's caused by the breaking of a neutron star due to magnetic dipole radiation. About 1 part in 100,000 of the energy that comes off a neutron star is in radio emission, and the neutron star's emission travels through our galaxy, which is ionized. So it's not a perfect vacuum. So the high radio frequencies around 850 megahertz in this diagram have arrived at the telescope slightly earlier than the 820 megahertz radio emission. And we call this pulse dispersion. And it turns out, although it makes our job of finding pulsars a lot harder, it's actually your friend, because most radio interference is not dispersed. So you can use this as a discriminant. So my great love is the Parkes telescope. And it's a 64-metre instrument in New South Wales in Australia, about 3,000 square metres of collecting area. And back in 2001, this telescope was doing a survey of the Magellanic Clouds, looking for radio pulsars, and an enormous burst of radio emission struck the telescope. And in this diagram, or the red photons are the low radio frequency waves, and the blue are the high frequency. The blue hits first. It got focused in the radio telescope, and it was so bright that it actually lit up 3 pixels in the Parkes multi-beam receiver. By a strange coincidence, in the brightest pulse, it was so bright that our software considered that it must be interference, and it deleted it. And that data was never processed. But fortunately, it was bright enough to be found in 2 side lobes. So the Lorimer burst, which is arguably one of my greater discoveries, was almost deleted by the software we wrote to handle interference. So you've got to be very careful about your a priori thinking. And the thinking was, if anything that bright hits the telescope, we already know about it. And since all pulsars repeat, we must know about them. And the idea that there were things that would just flash once and go away was a bit alien to our thinking, if you'll pardon the pun. And so this is where the 13 beams were pointing on that day, and the brightest pixel was this one. That got deleted by the software, but luckily one of the side lobe detections was here. And I'd just written some software to enable us to plot these things, and Duncan Lorimer explained to me that he had a new potential detection, but he wasn't sure if it was real, and had I ever seen anything in 2 beams before? And I said no. And we put this plot up, and I was just completely blown away, because this sort of perfect dispersion sweep going across. And I didn't know any cosmology back then, and we realized that the beam was actually missing the small cloud. And when you added up the number of free electrons between us and this pulse, it was about 300 megaparsecs away. So not only did somebody who'd always lived in our own galaxy and studied things in our galaxy had to learn about cosmology, I realized that this pulse was something like 10 to the 10 times brighter than any neutron star we'd ever seen. And so I wondered whether or not it could possibly be real. And I had to wait many years for anybody to find any more. In the meantime, I had a student, Sarah Burks-Ballore, who was looking for more examples of the Lorimer burst, and she managed to detect the local microwave in the visitor center, and it had this nice property that it lit up all 13 beams of the Parkes multi-beam receiver. So we knew it wasn't extraterrestrial, but it had uncannily around about the same dispersion sweep as the Lorimer burst. So I thought that my first science paper was actually going to have to be retracted. And unfortunately, nobody else could seem to find any of these Lorimer bursts. But I met Dan Wertheimer, and he'd explained to me that you could build these really cheap spectrometers out of these things called IBOBs, and there's a happy ending to this story. So interference has been around for a long time. This is Groth-Reber's original map of our galaxy, and you can see all these little spikes here. They're not actually pulsars or fast radio bursts. They're actually just sources of interference. And so we've been fighting interference for a great deal of time in astronomy. And the Parkes multi-beam receiver has this wonderful property that any near-field interference lights up all of the pixels. And what I've done is I've plotted amplitude versus time for the first 12 beams of the multi-beam receiver. And you can see that whenever there's a little bit of scruff, as Jocelyn would say, it's actually replicated in all of the other pixels. And you can actually use this to remove local interference and just leave behind the astronomy. And so that's one of the great strengths of the multi-beam receiver, and one of the reasons it sort of dominates the fast radio burst discovery rate. So this is actually an observation of a pulsar down here, but if we left all the interference in, it would look like that thing at the top. And so we can use this common signals to remove it, and that unveils the sort of true universe outside of your focal length. And so here's an example of taking that technique to an extreme where Vincent Morello, who's now at Manchester, looked at every single frequency channel. There's actually 1,024 in the Parkes telescope, and he removes common signals on a channel-by-channel basis. We didn't used to have enough computational power to do that, but we do now. And this is the latest FRB from Parkes. You can see there's a sort of a horrible sort of mesh of interference and so on underneath that, but using Vincent's techniques, he can actually reprocess that data, and it reveals this beautiful FRB, fast radio burst. This one's incredible because it has a dispersion measure of 2600. That puts it at a distance of a Z of about 2.5, and a luminosity distance well in excess of a gigaparsec. So there's now 27 FRBs that have been discovered from 5 different telescopes. That comes as a great relief to us at Parkes, because we wanted other people to find them, but not often enough that they would take away our glory. And this is some of the examples of them. Some of them are double peaked, some of them have scatter tails. This one here was the second one after the Lorimer burst to be discovered by Dan Thornton. And the one on the top right is by the Molonglo telescope, which has the first one to be found using an interferometer. So we remodeled this old telescope. It has 18,000 square meters of collecting area. It's 1.5 kilometers long, and it has a Fresnel scale of 14,000 kilometers. So anything it detects in just a single beam, it has to be that far away. It's recently found 3 fast radio bursts, and Manisha's PhD describes that. Here's where they are on the sky. It's galactic coordinates. We actually spend a lot more time surveying the galactic plane than we do out of it. And it seems that fast radio bursts avoid the galactic plane due to some combination of scattering of the signals, the increased sky temperature, and the fact that interstellar scintillation can amplify you greatly when you're off the plane, but not when you're on it. So what are they? Well, they're coherent emission. Otherwise, the brightness temperature is ridiculously huge. There's of order of 3,000 happening every day in the sky that are above 1 Jansky milliseconds. A Jansky is 10 to the minus 26 watts per square meter per hertz. If you extrapolate out to the universe, it seems like there's about 1 per galaxy per 1,000 years. But if each one repeats, that rate is very low, so they're very rare. So if they're aliens, I almost fell off the stage when I said that. they don't have to arise in galaxies very often. The dispersion measures are so large that they're at cosmological distances. And there was this fantastic discovery at Arecibo of FRB 121102, and this FRB repeats, which is remarkable. And it repeated so often that they managed to catch it using VLBI and the VLA, and they identified the host galaxy, and it's got a very firm luminosity distance of 870 megaparsecs, whereas the average pulsar is like a kiloparsec away. So this is about a factor of 1 million further away. The luminosity is greater by some 10 to the 10 to 10 to the 12 times more than pulsars. And so you can imagine if you're writing a telescope proposal and you say, oh, we know about these things called pulsars and they give off pulses, I'm going to do a survey to find things that are 10 to the 12 times brighter, what the time assignment committee would do to you. You wouldn't get any time. But remarkably, these things seem to exist. The favoured models are things like magnetars, because if a magnetar spun at a millisecond and had a 10 to the 15 Gauss field, you can generate an enormous amount of energy, and we wave the magic wand and hopefully get a pulse every now and then. It turns out an FRB has almost exactly the same flux density as the brightest quasars, but they're only on for about a millisecond, whereas quasars are on continuously. And then, out of desperation, we can push the alien button to explain them. And one of the reasons you might be tempted to do that is that I think Jim first produced this lovely diagram that showed you how bright a pulsar is, and the FRBs are those black dots up there, and there's now even some beyond that black dot. This is diagram's a little bit out of date. So there's obviously coherent emission going on, but taking a model that works for a neutron star and then getting a factor of 10 to the 10 or 10 to the 12 increase in luminosity is very difficult. And it's where we've had enough trouble trying to understand the pulsar emission mechanism. The FRB emission mechanism is 10 to the 12 times harder. So recently there was a paper which gathered a lot of press attention, and maybe if you're a Harvard professor, you can do this. I'm not sure you can do this from Swinburne. If you look into this paper, then it requires insanely advanced technologies from cosmological distances. You need to have telescopes the size of planets, collecting energy from their sun at 100% efficiency and shining it in your direction. I think this is unlikely only because the historical record shows that when pulsars were first discovered and posited to be little green men, they weren't. And this will probably be the same for this this model, but it's a hell of a lot of fun to do the maths. And if you think about it, there's two very simple ways you can transmit. So you can either concentrate all your energy in radio frequency and have that power on for all the time, or you can flip it around and do a very intense burst of radio emission across a very wide frequency range, but only for a delta function in time. And because of the uncertainty principle, the product of these things is better be bigger than one. But if you did something like took a nuclear weapon and detonated it, you get an electromagnetic pulse that lasts for about a microsecond. And if you look at the fast radio burst widths, they're usually around a millisecond, but there's one that was very close where you could infer that the intrinsic width was about 80 microseconds and that was limited by interstellar scattering. So if you had a nuclear weapon and you put it at the focus of Arecibo, which may seem like a terrible thing to do, and you detonated it, and somehow the structure survived for long enough to reflect your electromagnetic pulse, you would get an amazing burst of radio emission which would travel across the galaxy, and you could probably see it anywhere in our galaxy with an Arecibo-like telescope. Unfortunately, an Arecibo telescope only points to about 10 to the minus 7 of the sky. So the probability that this is happening very often is kind of rare. But these are fun games to play. If you actually look at if you're an alien wanting to transmit, you can either do it by doing a hyper-narrow line, or you can give it a hyper-narrow pulse. And if you look at the radiometer equation, the bandwidth and the time are both under the square root there. So it doesn't matter which way you do it, for the same amount of energy, giving off, there's no benefit between doing narrow frequency or narrow in time. So there's already a project called AstroPulse that Dan and his colleagues are looking at with Arecibo, where they look for hypernarrow pulses. It takes a lot of computational time compared to looking for spectral lines. And you've got to do a whole search in dispersion measure space, which makes it rather computationally demanding. Nevertheless, for sort of microsecond-wide pulses, it's feasible in real time with a whole bank of GPUs. So the Breakthrough Listen at Parkes project is looking for aliens, as you know and just heard. There's no reason we can't tap off the data and look for fast radio bursts at the same time. You can use clever eigenvector decomposition techniques to remove the radio frequency interference to boost your sensitivity, and you can do much better than we've been able to do in the past because of the brilliant instrumentation that's being installed there. So can FRBs be aliens? Well, I kind of doubt it. If you look at the repeating FRB, it's in a very hostile radio environment that's about 10 to the 5th times brighter than the Crab Nebula is in the radio. If I was an alien, I don't think I'd want to live there. But on the other hand, humans have the technology to already generate FRB-like signals and beam them out using planetary radar or atomic bombs on the focal point of telescopes. And so what is the log n, log s of alien FRB emitting civilizations? Well, I don't know. If you do the maths at Proxima, you could easily detect an FRB from there using the Parkes telescope, but the dispersion measure is so low, it's actually in our zero dispersion measure throwaway bucket, so we'd have to think about that a little bit more carefully. Ron's been trying to do that with pulses from the moon. It's quite a difficult experiment, but not impossible. And if you look at the future of FRB searching, there's some really neat telescopes coming online. ASCAP, CHIME in Canada, which should find between 1 and 10 a day, and a bunch of others, and hopefully Breakthrough Listen will contribute to this. Thanks.
Questions for Andrew? Matthew. Sorry.
Charles.
Somebody was doing it here. Way over there by the light.
Hi. If we assume that this isn't little green men, and that the pulse is 80 microseconds wide, does that not suggest that the physical emitter has to be less than 80,000 feet in scale?
Yes.
And does that inform the astronomy? Something like your magnetar is actually that small?
Well, there's pulses from the Crab pulsar that are only a nanosecond wide, so 80 microseconds isn't really a particularly difficult scale if the emission's coming from neutron stars.
Any other questions for Matthew?
So,
Sorry.
just accepting that these are at cosmological distances for the reasons you said, have you done a log n, log s plot, and does it make sense to you? Have you compared the distribution on the sky with the amount of time you spend on various positions on the sky? And
Yeah, so the log n,
is it consistent with isotropic?
with 27 objects, the log n, log s isn't amazingly compelling as
You read
yet.
some of the old
But
cosmology papers?
it's more like -1 than -3 halves.
Yeah.
And because of that, using a small diameter telescope is no worse than using a large one because your field of view compensates. So I think the future of fast radio burst searching may be sort of with backyard things. And there's even a proposal to use cell phones, which is probably not going to happen. But the smallest element I've seen that can detect an FRB is 12 meters, and there's no reason to think that you couldn't do better than that.
All right.
So I don't think I kept up with the news on this, but whatever happened to the interest in kind of quantized dispersion at a consistent
The numerology.
the multiplier where the dispersion was quantized. What happened with that?
It was garbage.
That's the technical answer. All right. Any other questions? Yes, Ron. Way over there.
Despite the small number of objects, I thought I'd make a follow-up comment on the attempt to interpret the source counts, which
Did Jamie ask
the
you to
evidence
make some
favors
concluding?
something flatter than Euclidean. Now, you might want to think about that, guys, because these are in the universe at cosmological distances. It is very hard to do anything that makes it flatter than Euclidean. Normally, we find steeper than Euclidean because there's always counterparts of the strong sources which are at greater distance, and any evolution makes it stronger. One thing can make it less than Euclidean, and that's if the population is bounded and doesn't extend continually. So there are some models that say all life will be extinct. There can't be any life in the early universe because the hostile environment has sterilized it. So if you like aliens, you might like a flat source count.